And our next talk, and the very last talk of ISMM'26, is going to be from Bijan Tabatabai, and he's going to talk about bandwidth speaks, we listen. Dynamic memory interleaving for tiering. Thank you.
Hi, hello. I'm Bijan Tabatabai, graduate student from University of Wisconsin-Madison, and today I'll be talking about our work on dynamically interleaving data to make effective use of a system's memory bandwidth. This work was done in collaboration with Micron. So memory scaling is not really keeping up with compute. On this graph, we see that the number of CPU cores on processors shown in purple is growing at a fast rate. However, memory capacity per core, shown in blue, is not quite keeping up. Similar trends are true for bandwidth per core as well. Luckily, CXL is a relatively new memory technology that aims to address these scaling issues. So CXL is a protocol that allows for cache-coherent memory expanders over the PCIe physical layer. This allows systems to more cheaply add memory capacity compared to adding a new memory channel, helping alleviate scaling issues. Similarly, it increases the bandwidth available on the system. However, it comes at the cost of higher access latency when compared to local DDR memory, which can lead to significant performance penalties if not used correctly. So the typical way that systems make use of CXL is called memory tiering, which makes use of the expanded memory capacity while minimizing the access latency. Memory tiering does this by first identifying which pages of memory are frequently accessed or hot and infrequently accessed or cold. With that information, the system makes sure to promote the hot pages to local memory and demote cold pages to CXL memory when the local memory is full. That way, in the common case, memory access go to local memory while still using the capacity of the slower CXL memory. This is similar to caching, with the main difference that data can be accessed directly from CXL without bringing it into local memory first. So tiering works well when the bandwidth of local memory is underutilized. However, when running bandwidth-intensive workloads, such as maybe matrix multiplication, putting all the hot data in local memory will oversaturate the local bandwidth while leaving the CXL bandwidth underutilized, leaving performance on the table. The solution to this is to interleave the hot pages between the local and CXL memory when under bandwidth pressure. That way, the system can utilize the combined bandwidth of the system. The current way to do this that's available in systems today is static interleaving. With static interleaving, the user specifies a system-wide ratio to allocate application pages with across local and CXL memory. However, because pages are not moved after they are allocated, static interleaving cannot adjust to changes in workload behavior. So, for example, imagine we have some oracle that knows all of this and decides the static interleave ratio for each workload individually. If a workload begins that uses only 75% of the local bandwidth, the oracle will just put all of the application pages in local memory. If another identical workload begins, the oracle will interleave its pages to utilize the aggregate bandwidth of the system. Currently, this is all fine and good. But if the first workload terminates, the local bandwidth is now left underutilized, and the second workload suffers from the higher CXL access latency for no reason. So what we want is a memory policy that dynamically interleaves application data between local and CXL memory based on the bandwidth demand of the system. A potential solution is a research system called colloid. When under memory contention, colloid will migrate pages until the access latencies of both nodes are equal, which will minimize the average access latency to memory. I'll demonstrate how this works with these example mock bandwidth latency plots. So colloid starts, like other tiered memory systems, by placing all of the data in local memory. As traffic goes to local memory, it goes up this bandwidth latency plot. If enough traffic is sent to the local node, its latency will be higher than that of the remote node. Colloid will detect this and then migrate hot pages from local to remote memory until the latencies are about equal. Consequently, the bandwidth utilization of the system increases. The problem with this is that when under bandwidth pressure, such as i.e. after the knee in this bandwidth latency plot, small changes in bandwidth result in large changes in latency, making the calibration difficult. So this can be seen by looking at the bandwidth utilization of colloid when running the bandwidth-intensive LBM workload compared to using the ideal static interleaving ratio for the workload. The bandwidth utilization when using the ideal static interleaving ratio for this workload, shown on the left, is quite stable at around 425 gigabytes per second of total bandwidth. However, Colloid's bandwidth utilization, shown on the right, is much more erratic. Because Colloid keeps moving data back and forth from local and remote memory, as a result, it only uses about maybe 350 gigabytes per second of bandwidth on average, and is 37% slower than the ideal static interleave ratio. So, Colloid is not really sufficient for bandwidth-intensive applications. It's leaving a lot of performance on the table. We want a new policy that treats bandwidth as a first-class priority and not just a convenient side effect. We propose a policy that does this called dynamic memory interleaving, or DMI. So let's talk about its design. So the goal of DMI is to maximize the system's bandwidth utilization, which we found experimentally results in performance much closer to the ideal. It does this by continuously adjusting how data is interleaved based on the measured bandwidth utilization. DMI is composed of two parts, the calibrator and the migrator. The calibrator monitors the system's bandwidth utilization and uses that information to determine how much to change the interleave ratio with the step selector, and how often to update the interleave ratio with the interval selector. It is implemented as a user space process. The migrator, which lives in the kernel, takes the ratio calculated from the calibrator and interleaves the application pages to achieve that ratio. The migrator also monitors if local memory is full and demotes cold pages to make room for interleaved hot pages. So the algorithm that the calibrator uses in the step selector to determine the interleave ratio is pretty simple. In this graph, we show the interleave ratio in orange on the left axis and the bandwidth in green on the right axis. The step selector starts conservatively with an interleave ratio of 100% local memory. Then, once the calibration period, it considers the largest sampled bandwidth for that period and changes the interleave ratio by some step size. If the bandwidth for this period is greater than the last, the previous step is considered good, and the step for this period will be the same as the last. Otherwise, if the bandwidth decreases, the step for the period is reversed and has half the magnitude. And eventually, it will zero in on the ideal ratio. If a change to the bandwidth demand is detected, this process is restarted to find the new ideal ratio. So an important parameter for the performance of DMI is how long the calibrator should sample the bandwidth before updating the interleave ratio. We call this parameter the bandwidth measurement interval, and it's determined by the calibrator's interval selector. Unfortunately, the best bandwidth measurement interval depends on the workload being run. We show this by running two bandwidth-intensive workloads, Cloverleaf and GapBS SSSP, with DMI using different measurement intervals, fixed measurement intervals. The plots here show the interleave ratio that DMI chooses over time, with the ideal ratio for the workload shown by the horizontal line. With Cloverleaf, a short bandwidth measurement interval of 1 second pretty quickly converges to the ideal ratio. And longer measurement intervals slow convergence, resulting in the longer runtime. Now let's look at the SSSP workload. And note that the grayed out portions here represent the startup portion of the workload. So here, a 1 second bandwidth measurement interval being used results in the calibrator being pretty erratic in choosing the interleave ratio. This is particularly bad because every time the interleave ratio doubles back, we are taking data we just moved to one node back to the other. With longer intervals, the calibrator more smoothly converges to interleave ratio. However, if it's too high, like with the 30 seconds here shown in purple, it will take longer than necessary to converge. So a bandwidth measurement interval that is too small for a workload will work poorly because a calibrator will not have enough context for making a decision. So consider this graph of the bandwidth utilization of the SSSP workload over time with a fixed interleave ratio. So all of the changes in bandwidth are due to the application itself. If the bandwidth measurement interval is too short, the calibrator may not have enough context for the decision. So for example, let's say for one calibration period, we sample the bandwidth in the indicated region, and then we sample this other region for the next. In this situation, the calibrator will only see a drop in bandwidth, but not know if that drop is due to a change in interleave ratio or the workload itself. This results in erratic change in interleave ratio, as we discussed in the previous slide. On the other hand, if the bandwidth measurement interval is too large, as shown on the left, the calibrator will have enough context to converge correctly, but it will take longer than necessary to converge. On the right, we see that the calibrator doesn't reach the ideal interleave ratio before the workload ends. So we noticed that the bandwidth utilization of the workloads we analyze tend to be periodic. So we want some way to identify the fundamental frequency here of the bandwidth utilization to set the bandwidth measurement interval to that. Visually from the graphs, we can see that the fundamental frequency of cloverleaf is about 2 seconds, and for SSSP is about 10 seconds. But how do we find this programmatically? Well, for that we use the fast Fourier transform, or FFT. The FFT is a mathematical operation that transforms a periodic time-varying function into another function that describes the extent to which certain frequencies are present in the input. Note that while the output of the FFT is often plotted with the x-axis being frequency, we show it as the period because it's a more natural unit for our needs. So for example, here we show a plot of a sine wave with a period of 1 second, and the FFT of that function is non-zero at a period of 1 second and near zero elsewhere. Similarly, FFT of a sine wave with a period of 5 seconds is non-zero at 5 seconds and near zero elsewhere. And if we take the sum of these two signals, the FFT can clearly identify the two component sine waves. So because the bandwidth of the utilization of the workloads is periodic, we use the fast Fourier transform on the bandwidth samples to decide what bandwidth measurement interval to use. So on the left, we show the bandwidth utilization of our workloads cloverleaf and SSSP over time, which have a fundamental frequency, as I said, of 2 and 10 seconds. And then on the right, we show the corresponding output of their FFT. Again, on the x-axis, we show period instead of frequency. So the FFT of cloverleaf shows the strongest components at a period of 2 seconds, indicating that that's a good choice of the bandwidth measurement interval, which we visually said is true. Similarly, 10 seconds in the FFT for SSSP is the most dominant frequency, so we should use that as our measurement frequency, or measurement interval. Note that while there are other peaks in the FFT due to the bandwidth signals not being perfect sine waves, the fundamental frequency is still easily identifiable as the strongest component. It's important to note, though, that these bandwidth figures on the left are shown with a constant interleave ratio. However, with DMI, the interleave ratio will be changing, which changes our bandwidth measurements. Taking the FFT of a signal that we are modifying leads to some challenges for determining the correct bandwidth measurement interval. For the sake of time, we don't discuss these implementation details to solve them, but they can be found in our paper. So now we'll quickly talk about the migrator. The first of its responsibilities is to decide which pages should be candidates for interleaving. The migrator only chooses hot pages as interleave candidates, ignoring cold pages. This is because, being infrequently used, cold pages don't have a large effect on the bandwidth utilization, not really making them worth the cost of migration. On the other hand, since hot pages are, by definition, accessed frequently, migrating them has a larger effect on the bandwidth utilization of the system. So in addition to interleaving hot pages, it's possible that there may be too many cold pages in the memory node to interleave the pages effectively. In these situations, the cold pages are moved to the other node to make room for hot pages. This also has a useful property that when the interleave ratio is set to 100% local memory, DMI kind of falls back to the traditional tiering, because in that case, all of the hot pages will be moved to local memory while cold pages will be demoted to CXL. So now let's look at the evaluation. So we evaluate this on a 72-core Intel Granite Rapids CPU with 7 DDR5 memory channels totaling 260 gigabytes per second of read-only bandwidth. And we have 8 Micron CZ122 CXL memory expanders totaling 220 gigabytes per second of read-only bandwidth. And we compare the systems to a baseline of the ideal static interleave ratio that we found manually for each workload. So first, we look at how well DMI performs running a single bandwidth-intensive workload that can fit entirely in local memory. And then in addition to evaluating DMI against colloid and the ideal static interleave ratio, we also evaluate against Nomad and HMSDK, which are state-of-the-art traditional tiering systems. So the x-axis of this graph are the workloads being run, and the y-axis represents the runtime of the workload relative to the runtime of just putting all of the workload's data in local memory. So because Nomad and HMSDK leave all the workloads data, hot data in local memory, they don't make use of the CXL bandwidth, making them 50% slower than the ideal case on average. Colloid performs much better than them, because it does make use of some of the CXL bandwidth. However, because of its more erratic data placement, it's still on average 27% slower than ideal. On the other hand, because DMI can effectively find the interleave ratio, it performs within 5% of the ideal case on average. So to dig a bit deeper, we look at how well DMI converges to the ideal interleave ratio for a workload compared to colloid. So the x-axis on this graph represents time, the y-axis represents the interleave ratio effectively, and the ideal ratio for the workload is represented by the dashed line here. So colloid, plotted in blue here, is very erratic with its data movement and never really reaches a steady state. On the other hand, DMI, which I plot here in orange, reaches near the ideal interleave ratio in around 30 to 40 seconds and stays there for the rest of the application's runtime. In fact, a majority of the slowdown DMI has compared to the ideal case is due to the time it spends searching for the ideal ratio. So now let's look at evaluate our method of selecting the bandwidth measurement interval using the FFT. So the graph on top shows the interleave ratio chosen by the FFT approach, shown in orange, and the best fixed measurement interval that we found that we tested for this workload. And then the bottom graph here shows the chosen measurement interval when using the FFT approach. So with Cloverleaf, our FFT approach initially chooses an interval of 2.5 seconds in the beginning, and then 1.5 seconds as the workload speeds up due to having more bandwidth. Using the FFT approach allows DMI to converge about maybe 20 or so seconds after the fixed measurement interval of 1 second. With SSSP, the FFT approach chooses a measurement interval of around 15 seconds, and it converges in about the same time as a fixed interval of 16 seconds, which of the ones we've tested perform the best. As a result, the FFT approach performs within 1% of the best static interval that we found. So however, this approach is imperfect. The GAP-BS BC workload has a much more erratic bandwidth utilization than Cloverleaf and SSSP. And so like before, with a 1 second measurement interval, it's pretty erratic. And we found a measurement interval of 30 seconds works best for this workload. The FFT approach initially correctly chooses an interval between 25 and 30 seconds. But after some time, because of the erratic nature of the bandwidth, it drops to between 3 and 10 seconds, causing it to diverge a little bit for the interleave ratio. Despite this, at the end, it still recovers. And the FFT approach still results in performance only 3% slower on average than the best fixed interleave ratio that we found. So now let's look at how DMI handles changes in bandwidth demand. We do this by starting an instance of the LBM workload using 20 cores, and after 300 seconds, starting another instance using remaining 51 cores. The plot above shows the interleave ratio DMI chooses in orange, and the number of CPUs that are being active at time in blue. So here in the beginning, DMI approaches the interleave ratio with the first instance of LBM running alone. And then after 300 seconds, the second instance of LBM begins, causing DMI to decrease its interleave ratio to handle the increased bandwidth demand. And then at around 650 seconds, the second instance of LBM ends, and DMI returns to its original interleave ratio. Because DMI adjusts to the bandwidth demand of the system, it performs at least 4% faster than any single static interleaving ratio. So in conclusion, effectively utilizing the bandwidth is important for application performance. And static interleaving is insufficient for shifting bandwidth demands. We showed how to dynamically utilize system bandwidth DMI, which is on average 18% faster than colloid for bandwidth-intensive applications, and can also outperform static interleaving when the bandwidth demand is variable. The kernel changes needed for the migrator have also been merged in Linux since version 6.17, allowing this to be more easily used. Thank you. Any questions?
Yeah, interesting talk. So I've not read the paper, so you might have addressed this. So around about maybe 8 years ago, right, there was this whole line of research on DRAM caches, where you have die-stacked DRAM, and then you could add that as a cache level to normal processors. And people then studied this very similar problem, right? So you have this DRAM cache level and then the memory, and there are these two tiers. And then the question is, how can you actually consider bandwidth to use this die-stack DRAM cache effectively? So have you looked at that line of research? And so in particular, I'm understood what is actually different in these two contexts.
I don't think I've seen work in related to that context. In the paper I cite similar work in terms of like NUMA machines. And basically what I found that either for those works specifically, either they rely too many on the properties of being a NUMA machine rather than CXL, or they're just not as sophisticated. But for the die-stack DRAM, I can't specifically answer that question.
We've got time for another question. Would you mind me asking a terribly naive question?
Please.
This is a little outside my area, so I missed something crucial at the beginning.
Sure.
So what I got was that in a place when you're choking the memory bandwidth, you want to, I assume that the goal here is to restrict the use of the memory bandwidth by using interleaving of the, or putting some of the hot pages across the CLX so they're not using the memory bandwidth. Is that,
well,
they're reducing their memory bandwidth pressure?
Yeah, it's reducing the pressure. Let me see if I could find the slide.
Yeah.
So like here with basically all the memory accesses are going to the local node, but it's higher than what it's more requests than what the memory controller can handle. So you have queuing effects, which increase the latency, which limits the bandwidth. If you instead move some of those requests to CXL, now you have maybe about the same amount of bandwidth being served on the local node, but now you have basically, you've added another line for people to queue, and you could serve more requests that way. Does that answer your question?
Yeah, it does. Yeah.
Okay.
But I mean, it's slightly counterintuitive that you're putting your hot pages in the remote place. But
Right.
I totally get it. And that was what tripped me up. Thank you. Yep. We've got time for another question.
Very, very interesting talk. I wonder, is there a possibility that because of those migrations, you end up causing more, you get like a higher bandwidth, but basically you caused like more last level cache misses because you kept migrating stuff?
Like basically, does the cost of migration hurt you more than the bandwidth benefits?
Yes, but actually I now realize that my question made no sense. I'm sorry for that.
Okay. I mean, it's a concern.
No, what you are saying makes sense. My question was different, but.
Oh, okay. Yeah, sorry.
Feel free to ask.
Oh yeah, so yeah, there are costs of migration. We found in this, especially because we had only one thread doing migrations, that one core out of 72, we didn't see a big impact on the workloads that we're running. Maybe if you sped it up where maybe the workloads are much larger, you want more migration threads to get it to where it needs to be quicker, then you might have to consider the trade-off of how many threads are used to migrate versus not. But we didn't, with our one thread, we didn't see that many downsides of migrating.
Just one last comment. I thought the way you used the FFTs was really cool.
Oh, thank you.
Coincidentally, we did something like that in a large-scale service in Google, my colleague and I, and it worked very, very effectively on this very diverse, very large workload. So it's really cool to see you doing something like that.
Oh, thanks.
All right. Any last questions? In that case, let's thank the speaker for a great talk.
Thank you.
Unless you ask me, you can do.
I just wanted to thank the audio visual team for sorting everything out and being brilliant, and all the PLDI organisers and all the speakers, invited speakers. Young Ho and Tomohiro have done an amazing job of putting together a program committee and program for this, and yeah, General Chair for for ISM is actually quite an easy job because PLDI do nearly everything. So thank you, everyone.